the main reaction type that carboxylic acid derivatives such as amides, esters, amides, acid anhydrides, and acyl halides will undergo is referred to as nucleophilic acyl substitution, where what happens in a nucleophilic acyl substitution reaction is that we start off with our so-called carboxylic acid derivative, and the carboxylic acid derivative is bonded to a heteroatom, which acts as a good leaving group. So this heteroatom here, this leaving group in our carboxylic acid derivatives, is going to be a nitrogen, a halogen X, or an oxygen atom. And what will go on in the reaction is that a nucleophile will come in, which I'm going to abbreviate as NU ... to represent the lone pair of electrons that the nucleophile is going to use to attack the electrophilic carbonyl carbon. And in the presence of an acid catalyst here, which I'll abbreviate as H+, what will ultimately happen in the reaction is that the nucleophile will at some point in the reaction mechanism come in. Ultimately, the leaving group will leave over the course of a few steps here, and that will ultimately result in replacement of the leaving group from our carboxylic acid derivative with the nucleophile. Now, we could spend literally weeks and weeks going through all of the different mechanisms for specific carboxylic acid derivatives reacting with specific individual nucleophiles to give a variety of different so-called nucleophilic acyl substitution products where we're substituting out a leaving group from the acyl group with a nucleophile, a new nucleophile onto that acyl group. We could go through the specific reactions for literally weeks about that. But the good news for us is that rather than trying to memorize weeks and weeks worth of specific reactions, instead there's a general mechanism that these reactions are going to follow. And by learning that general mechanism, we can then apply that to any specific situation that might be thrown our way, as long as we recognize where we need to apply that general mechanism. So, speaking of knowing when to apply the general mechanism that we're going to talk about here, this mechanism that we're going to focus on is going to be applicable in situations where there is acid present in the reaction mixture. So we have an excess of protons here available to react. We will later look at a general mechanism for base catalyzed nucleophilic acyl substitution. So that's why it's important to, as you start to analyze these, the first thing you'll want to do when you sit down and start looking at these reactions, you say, okay, I have a carboxylic acid derivative, I have a nucleophile, and then from there you need to say, is there acid present, or is that nucleophile an anionic or basic nucleophile? That is going to drive what the mechanism is that you need to be thinking about occurring in the reaction. So in cases where we have an acid catalyst present, we are going to follow the general mechanism that we're going to go through in this particular video. In the next couple of videos after this, we're going to do some problem solving or examples of applying this general mechanism that we're looking at here. So if we get this mechanism down really well here, that's going to make our job easier in the future and is going to enable you to tackle the types of problems that you will run into regarding nucleophilic acyl substitution, because I can't possibly, in the time that's available in these class sessions, go through all of the different carboxylic acid derivatives on all of the different nucleophiles. So that's why it's important for you to recognize the general features of the reaction and generally recognize what you need to do here so that you can apply it toward any specific situation that you might be thrown without having to memorize a whole laundry list of reactions. So let's go ahead and take a look at this general mechanism for acid-catalyzed nucleophilic acyl substitution. We are going to go through this mechanism with a generic carboxylic acid derivative as our starting material. So our generic carboxylic acid derivative I'm going to use is going to look like so, where R there could be a hydrogen or carbons, whatever group you want over here. And then I'm going to plug in LV as whatever our leaving group will be. So this is defined as our carboxylic acid derivative. So in all of those carboxylic acid derivatives that we looked at, the leaving group was always a heteroatom. It was always an oxygen, a nitrogen, or a halogen there. And that's no coincidence because all of those are electronegative atoms that are ultimately going to be relatively good leaving groups. So we will react in this particular reaction we are going to say that we have our generic nucleophile. I'm going to make this a neutral nucleophile, meaning there's no formal charge on that nucleophile. That nucleophile, in fact, I'm going to put a hydrogen directly bonded. So this could be like an alcohol or something like that, where you have an OH bond present in the molecule, or an NH bond, something where you have a lone pair of electrons on your nucleophile and there's also a hydrogen bonded there. And then we also have our acid catalyst present. And the acid catalyst is what you will really want to be looking for in determining that this is the mechanism that you need to use in this acid-catalyzed nucleophilic acyl substitution. So we are going to work through the mechanism here to show how we go from the starting material to the final product. But the final product is always going to correspond to having replaced the leaving group, the heteroatom and whatever it's directly bonded to over here, with the nucleophile, which is substituting its way into the molecule during the course of the reaction. So looking at the mechanism for this reaction, I'm going to go ahead and zoom out here a bit on that information so we have plenty of room to work with the mechanism. We'll start with our carboxylic acid derivative, and anytime we have a relatively strong acid present as a catalyst for a reaction, the way that that acid is going to function is at the very start line of the reaction, the first thing that's going to happen is going to be protonation, because acid-base reactions are very, very fast. And so as a result, if there is acid present in a reaction mixture, that acid is going to swoop in and it is going to react with whatever you have available as some lone pair electrons that can come over and grab that proton. So lone pair electrons that we have available, carbonyl group is going to be the best set of lone pair electrons to come over here and grab that proton from our acid. And that's going to lead us down our path here to now having our oxygen out with one set of lone pair electrons. The other set of lone pair electrons became this covalent bond to our proton. Now we have protonated our carbonyl group. We need to put a positive charge on that oxygen. And now at this point, what is going to happen here is that we have made our carbonyl carbon now super electrophilic, because now at our carbonyl carbon, we have this oxygen that not only is electronegative, but it has a positive formal charge on. That positive formal charge means that that oxygen is very electron deficient. That oxygen does not want to be electron deficient because that is a very electronegative atom. So it's going to be strongly, strongly pulling electron density toward itself. We could in fact draw a second resonance structure here as well, where we could show that we can move the pi electrons up onto the oxygen to make that oxygen have no formal charge, and then put a carbocation right here. That also illustrates to us why this carbon is very much electrophilic, why it is very electron deficient, and hence eager to be attacked by the nucleophile. So our nucleophile that we had here was we have that hydrogen directly bonded to our nucleophile. Our nucleophile is going to come in and use its lone pair of electrons to attack the carbonyl carbon. That is going to force, in order to avoid going over that tetrahedral of that carbon, the carbonyl electrons to go up onto the oxygen. Coming on down the path here, I'll go ahead and write out in words what was happening here in this step. And that step was that the nucleophile was attacking the electrophilic carbonyl. And now we have a tetrahedral intermediate, a carbon that has 4 groups bonded to it, in other words, an sp3 carbon. So our sp3 carbon, that carbon that I'm highlighting in green here in our starting material, and the carbon right here that I've highlighted in green in our product, now has a single bond to an OH group and a new bond that I'm going to put in blue here to our nucleophile. Our nucleophile used its lone pair of electrons to make that bond, so the nucleophile no longer has a lone pair of electrons, but it still has that proton bonded to it. And the nucleophile originally had no formal charge. Now that it's formed a covalent bond here, we would expect that nucleophile to now have a positive formal charge on it. Also, in the interest of retaining the net formal charge, when we started off this step, our net formal charge here going into it, what I'm highlighting here, net formal charge of all of this was +1. So therefore, what comes out of that also has to have a +1 formal charge. So somewhere in here, we need a +1 formal charge. The only place for that to go is onto that nucleophile. So now what's going to happen in step number 3 of the mechanism is that in step number 3, that nucleophile would really not like to keep that proton around for any longer than it has to. And so in step 3, that nucleophile is going to be deprotonated, and this will reform the acid catalyst as well at this step. So step 3 is going to be deprotonate the NUH. So we're going to remove that proton right here from the nucleophile that is attacked here. You could imagine that like water or something like that would come in, it would have a proton here for a base to come in and grab. And our base that we can use here would be possibly another unit of our nucleophile, because remember that nucleophiles generally are not only nucleophiles as one role that they can play, but they can also act as bases. So nucleophile comes in, grabs a proton, making that nucleophile really acting as a base in this case because it's grabbing a proton. That forces the bond between the proton and our NU that had come in here and formed a bond. And so our product of this step then would be, we'll have our R group, we'll have our LV, what's ultimately going to be the leaving group, we'll have our hydroxy group, and now we will have our nucleophile, and that nucleophile will now have a lone pair of electrons associated with it. So it will no longer have a formal charge because now it's back to its original state where it was neutral up here at the top, where it had a lone pair of electrons and a bond to hydrogen. Now it's got a lone pair of electrons and a bond to a carbon. So no formal charge on that nucleophile. And our other product of this reaction would be our conjugate acid that resulted from forming a bond between our base over here on the right-hand side of the screen with our proton. So that gives us NuH2, and then there would be a positive formal charge because that nucleophile or base grabbed that proton to give it an extra covalent bond and positive charge on it. So now we have here this as our intermediate at this point in time. We're not quite to the final product yet because what we need to do here is, since we have that acid catalyst present, the acid catalyst is going to come in, and our leaving group, we said that our leaving group was always halogens, oxygens, or nitrogens. All of those have lone pair electron or electrons on them. And so what happens is that since all of those have lone pair electrons on them, when we have that leaving group in the presence of our acid catalyst, what can happen is that that set of lone pair electrons from our leaving group can come in and grab that proton. And so step 4 here is protonation. So we're going to protonate the leaving group. We are preparing the leaving group to leave by protonating it. Now, some of you might be looking at steps 3 and 4 here and saying, we deprotonated one portion of the molecule, then we protonated another portion of the molecule. Couldn't we put those steps into one and done a proton transfer from directly the proton that is attached here at the end of step 2 and move that proton onto the leaving group? Yes, you could have done that as well, doing an intramolecular proton transfer here rather than what we showed, which is an intermolecular proton transfer. We're transferring the proton completely out of the molecule and then transferring a proton in from somewhere else. We could have done that intramolecularly, showing the lone pair electrons in the leaving group, grabbing the proton from our what came in as the nucleophile up here. So either way you want to do it, it will work. So we will go ahead and draw out our structure here that we're working with. So now I have the leaving group with a new covalent bond to the proton, and that's going to make that leaving group have a positive formal charge then at this point. And now that that leaving group has a positive formal charge on it, that is going to make this an even better leaving group than it was before. So I'm going to put this in and label it as a great leaving group now. And the reason it's now a great leaving group is that if we break it away, it is going to leave as a neutral molecule. It is not going to leave as a cation. So it's going to gain stability by doing that because it will no longer have a positive formal charge on that electronegative leaving group atom. And so that makes this breakage favorable because the bond is both weak and the product resulting from that, this leaving group product that has this proton associated with it now, is going to be a stable neutral molecule. And so that's in fact what's going to happen is that in step 5 of the mechanism, what's going to happen is that the leaving group will leave, the leaving group breaks away, and the carbonyl is going to reform. So let's go ahead and show that carbonyl reforming by taking the lone pair electrons from the oxygen, bring those down to make your carbonyl group as the leaving group leaves. Now let's go ahead and draw out what would result from this. So we have our carbonyl group. Carbonyl group still has that extra proton on it. We haven't done anything to get rid of this hydrogen atom here that I'm highlighting in our reactant. So that hydrogen is still over here on the product side. We have our carbonyl group. And then our carbon that's directly bonded to that carbonyl group is the carbon right here, which is going to correspond to the one right here that I've highlighted in red in both the starting material and the product here. So that carbonyl group directly bonded to our R group over here, directly bonded to the nucleophile, which I need to plug in as well. So I'm going to plug in nucleophile NU. And then our leaving group is going to be LVH for the leaving group that has broken away. Now, there would be a positive formal charge on the oxygen because our carbonyl oxygen has that proton, and hence positive formal charge would be the calculation there. And now down to, I promised you, the very last step of this mechanism. Coming up here to get to our final product. The only thing that we need to do is a deprotonation step because we have this extra proton here. If we can get rid of that, we can get rid of that positive charge on the oxygen. And so, in order to accomplish that, we're going to call step 6 here, not so creatively, deprotonation. And deprotonating, we can use to deprotonate our leaving group that is broken away with the proton would be expected to have a lone pair of electrons because when we broke this bond here, we broke that bond that I'm highlighting in red at the bottom of the middle of your screen. The electrons from that went onto the leaving group, so that would give us a lone pair of electrons to use to grab that proton. Alternatively, what we could also use is another unit of the nucleophile. So either one of those will work. What we really just need is a source of lone pair electrons to come in and grab that proton. And so I'm just going to do it with our starting material HNU. Use the lone pair electrons in the nucleophile to come in and grab that proton, forcing the hydrogen-oxygen bond to break. And that's going to give us the carbonyl that we see in our final product. So in this reaction mechanism, going through this series of protonations, nucleophilic attacks, deprotonation, more protonation, and leaving group leaving, and deprotonating again, what we ultimately end up with at the end scenario is that the leaving group is replaced with the nucleophile. That's the net effect of the reaction. As you look at this reaction mechanism kind of holistically, what we need to keep in mind here in the future as we are writing out these mechanisms is that you'll notice in this mechanism that at no point do we form products that have negative formal charges. And that is going to be true in general in situations where we have acid-catalyzed reactions. Acid-catalyzed reactions are going to disfavor the presence of anions because of the fact that we have that excess of proton cations. The acid-catalyzed reaction is going to avoid, generally at all cost, having any anions as products. So no anion products of any of these reactions, not even the side products. And that's why, rather than our leaving group here at the end of step 3, we might have thought or been tempted to take that leaving group and just break it away. But if we just broken it away without protonating it, it would have left as an anion. And that is very unfavorable because it's very unstable to have a negatively charged anion floating around in solution in this very acidic environment. So what's going to happen faster and more favorably instead is that this protonation happens so that then the leaving group can break away as a neutral molecule. So as you are going through these reactions, one of the basic fundamental premises of writing mechanisms out and thinking about how reactions are working is that when you are under acidic conditions, don't create anion products. That is something to kind of lock into your brain as you're thinking about how to logically go about writing reaction mechanisms. So this is our general mechanism for acid-catalyzed nucleophilic substitution. We will do this type of reaction by plugging in any of our carboxylic acid derivatives, such as our acyl halides, our amides, our esters, and our acid anhydrides. And we will go through this reaction mechanism with a variety of different nucleophiles, such as water, such as alcohols, etc., in the presence of acid catalyst. And this schematic that we will do will be the same in each case. So if we get really familiar with this general reaction mechanism, we can apply it to whatever situation we come across. That is the point of learning this particular mechanism.